I am Tamilselvi, Assistant Professor of Mathematics, Vellalar College for Women, E-Road 12. I present the topic on the subject topology. Topology is a study of properties of geometric figures or solids that are not normally affected by changes in size or shapes. The branch of pure mathematics that deals only with the properties of the figure x that hold for every figure into which x can be transformed with the one-to-one correspondence. By explaining the n explicitly is a topologies, where the topology is a study of concern with the natures and properties of geometrical figures. Topology was a term invented by Solomon Lefkowitz, a mathematician who was connected with early topology. Topology has frequently been called rubber band, rubber sheets, or rubber space geometry. It deals with the properties of geometric figures in space that remain unchanged when the space is changed. The only exceptions are that tearing the space is not allowed and the distinct points in the space cannot be made to coincide. Strictness and linear and angular measures of the planes are some of the properties that are obviously not maintained if the plane is disordered. Here in the figure 3, the two odd vertices, so it is possible to draw that the figure continuously without tracing edges. These are the examples of early topological questions, but these problems were the basis for modern topography, and therefore the questions and concepts therein are still explored in topological today. So these are the example of topologies which compared with the iron and mug and basketball and football. This is the definition of a topological space. A topological space is a pair of subsets x and tau, where x is a non-empty set and tau is a collection of subset of an x such that satisfies the conditions x comma pi which is belongs to 2 tau and satisfies the finite intersections and arbitrary union condition. Here the x, which is called an underlying set, and tau is a topology, and all the members of taus are called open sets. Some of the branches which is mentioned as point set topology and algebraic topology. In point set topology, there exists only a basic of a sets and subsets which are deeply concerned with connectedness and compactness. In algebraic topologies, which is derived from a combinatorial topologies, models, topological entries and relationships are algebraical such that the groups or the rings are explained. Here the subspace topology definitions, where Y is a topological subspace of an X, where X is a topological subset, where X and tau which is said to be an subspace of an X. The elements which is open set and the sets are said to be relatively open in Y. Next one, relatively open set. Y is a subspace of an X and A is a subset of an Y. Then A is said to be a relatively prime if and only if where the M which is belongs to 2X and the M is a open set X such that M intersection Y is equal to A. Also for the relatively closed set, Y is a subspace of an X and B is a subset of an Y. Then B is said to be a relatively closed in Y if and only if where n is belongs to 2x and n is closed in x if and only if n intersection y is equal to b. Here the neighborhood definition, that A is belongs to X where X is a topological space, then a neighborhood of A denoted by n of A is a subset of an X that contains an open set containing A. It satisfies the continuation function property and the continuous functions maps open or closed sets with X into an open and closed with Y. So here the connectedness, the general idea that all the space touches a point can freely be moved throughout the spaces to assume the locations of any other point. Connectedness, space that cannot be broken into a several disjoint yet open set. This can be differently known for the no separation space. Considered x is equal to x1, x2, where tau is equal to pi, x1, x. The space that cannot be broken or that have a no separation space is said to be a connectedness. Path connectedness which is connected at each of its point. This is a simple connectedness. Simple connectedness is which is free from a holes and the space where every ball can shrunk to the point. The space where every path from the point A to a point B can be deformed into any other path from the point A to the point B. This is a general connectedness. The topological space X is said to be a connector if and only if X is contained in capital X, where X is both open and closed, then X is empty or capital X. This is the example for a disconnected set. Here the set X which is equal to 1, 2, 3, 4 and the chow which is equal to empty set 1, 2, 3, 4, 1, 2, 3, 4. Let us consider the set A which is equal to 1, 2 and B which is equal to 3, 4. Here the A union B is equal to X and A intersection B is equal to empty. So this implies that B is a complement of A, and since A is open and then B is closed, but B is also open since it is an element of tau, and since it is neither X nor empty, X is shown to be disconnected. General compactness. A subset A of an topological space X is said to be a connector if A is contained in A, where A is both relatively open and relatively closed, then A is equal to A or empty. Path connectedness. Let A, B belongs to X and F which is mapping from the closed set 0, 1 to capital X, where F is continuous function, and let F of 0 is equal to A and F of 1 is equal to B. Then F is said to be path in X, and F of the closed set 0, 1, the image of the interval is a curve in X that connects A to B. Let X, Y which is belongs to X, where X is a topological space, then X is said to be a path connector if there is a path that connects X to Y for all X, Y. These are the some of the questions which rises for a path connectedness. And path connectedness, let A is belongs to A and B is belongs to C of A. Since X is path connected, so the XF is mapping from the closed set 0, 1 to X, where F of 0 is equal to A and F of 1 is equal to B. So the set B is either open or closed, but not both, since the closed set 0, 1 is connected. Therefore, A can be open or closed, but not both. This is an example. This is a contradictions which arise for that we take S is disconnected. So we conclude that every path connected space is also generally connected. Next one is simply connected. First which start from the homotopy definitions. Let F1, F2 be a paths in X that connect X to Y, where X, Y is belongs to capital X. Then F1 is said to be a homotopy to F of 2 if and only if which is mapping from H the closed set 0, 1 to the whole square to X, where X is continuous, such that the following hold true for X, T is lies between 0 to 1, where H of 0, T X, H of 1, T is equal to Y, and H of S, 0 is equal to F1 of X, H of S, 1 is equal to F2 of X. Here the mile maker for the first one graph and the second one graph, comparing to first one which is start, 0, 1 and second one for 1, 0. The function's H is called a homotopy connecting F1 to F2, and F1 and F2 are both belongs to the same homotopy classes. In a simply connected space, any path between 2 points can be deformed into any other spaces. Consider the closed loops, ones in which the starting and ending points are the same, then they must be all deformable into one another. One such closed path where we leave from the point A and return to it is to never leave it. This path is called a constant path and it is denoted by E of A. Let X be a topological spaces and X is belongs to capital X, then X is said to be simply connected if every X there is only one homotopy classes of a closed path. Since the constant path is guaranteed to be a closed path for X, the homotopy classes must be closed on EA. This is an example for a simply connected space. Next one is compactness. Before compactness, we refer the covering. Let X be a set A is contained in X and C is equal to the set of B alpha, where alpha belongs to the indexed set I, be an indexed subset of an A. Then the set C, which is said to be a cover of A, if and only if A is contained in the union of C, C belongs to the script C. If only a finite number of sets are needed to cover A, then C is more specifically a finite covering. Let X be a topological spaces and let C, which is equal to set of B alpha, where alpha belongs to the indexed set I, be a covering of an X. Then if for all C there exists an D such that D is contained in C and D is finite, then X is said to be a compact. Example of the spaces, this is not a compact, consider the real line. For the real line, we have considered the open interval n, n plus 2 where n belongs to the integers is clearly a covering of A. Removing any one interval leaves the integers value uncovered, therefore no finite subcovering exists. Here the removal of an interval, here the 2 is no longer covered. Here the locally compact topological spaces definitions. Let X be a topological space, then X is said to be a locally compact for all X belongs to X, such that for n of X is a compact. Note that every generally compact set is also locally compact, since some subset of the finally covering of the whole set will be the final covering of some neighborhood of an every X in the space. Here some of the questions raised for the compactness. These are the applications of the topologies. Topologies are applied in network theory, knot theory, and genus categorization. Here are the applications for a fixed point theorem. Here the closed interval 0, 1 is path connected, and since f is continuous, f of the closed path 0, n is also a connected. Suppose f never crosses the line y is equal to x, then let the closed interval a, b a interval containing some z's where f of a is greater than or equal to a and b is greater than or equal to f of b. Here we conclude that f of z is greater than or equal to z and greater than or equal to f of z, which lies from the f of z to f of z, since a path must connect the endpoints f of z is equal to z. Here the application of an conservation force. The work is done in changing an object position is said to be a path independent. Of a significant results of this type of force is that the work done is moving an object along the closed path is 0. Here the continuous for the conservation of force, which is work done which is not moving an object, is obviously zeros. So we can summarize that as to be 0. This is another way. Move along the straight line connecting those 2 points and then move back along the same path. The total work done during the journey will be 0, since the magnitude of both trips is same but the signs are opposites. Each transfer of the path is homotophically equivalent to transferring 1/2 of the closed path. Thank you.